to all?
Yes, sir. Yes, sir.
Okay, okay, thank you. So, if you have any queries, questions relating to my earlier talk yesterday, you can ask, or else I give some small recapitulation, short recapitulation of what I talked about yesterday. So basically, this talk is about PID. It's how we do the particle identification. Means in the previous talk from Raghu sir, Professor Shahu, you heard that there is this difference between rapidity and pseudo rapidity, and it is relatively difficult to measure rapidity because you do not have the PID information always. So that's why it's relatively easier to do the pseudo rapidity because it's more of a geometric quantity. So in this talk and also in the previous talk, I mainly discussed about how we can extract the information of PID. This is the particle identification, and by PID, what we generally mean is the mass of the particle, right? So how we because that is the one very basic thing that differentiates between different particles. So yesterday I introduced about the different ways of extracting the PID. So I just give a short recapitulation of what I said. That is, there are different detector response which can be related, which can be used or exploited uh, to extract information about the type of the particle or the particle species. So there is a DETX measurement, that is the energy loss, which is related to velocity of the particle, and from that you get different bands for different particles species, and using some kind of today I will discuss how you can actually quantify this separation. uh, you can actually cut out one particle from separate out one particle from another. Then there is a timing measurement, which is done by TOF, time of flight. And from there, this is also kind of a complementary to the DETX, where you also get the information about the particle species. Means if you have a pion and kaon, which are of different mass and at same momentum, of course, the kaon will take more time to traverse a certain path than pion. So you use these very rudimentary and fundamental principles to identify the particles. Next is this. This is the detector response of TRD, that is the transition radiation detector. Uh, that is, it emits when the charged particle passes through an inhomogeneous media. By inhomogeneous, I mean if the media has is a combination of two medium with different dielectrics, then the charged particle emits a photon, and that photon is then converted into a detectable signal. So overall energy loss, that is the ionization plus the energy loss from the photon, together it forms this signal for the transition radiation detector. And this detector assist or helps in separating out the electrons and pions. And then there is another mode detector which is based on the Cherenkov radiation principle, that is the HMPID, high momentum particle identification, and which you know that when the velocity of a particle is higher or than the velocity of light in a given medium, it emits Cherenkov, and the angle at which the Cherenkov radiation is emitted is also inversely proportional to beta. So utilizing that information also, you can you can actually separate out different particle species. So this was all based on the velocity. You can just loosely or roughly say that this kind of identifications were based on the velocity of the particle. And then there are calorimeters, and the calorimeters where you know where almost all the energies are dumped. Means the particle which travels to the calorimeter, it dumps most of all of its energy. So there are two types of calorimeter that exist, that are commonly used in our high energy physics experiments, that is the ECal and the HCal, that is the electromagnetic calorimeter and hadronic calorimeter. So in the electromagnetic calorimeter, the electrons and photon deposits their energy, and in hadronic calorimeter, mostly the hadrons, both charge and neutral hadrons, it deposits energy. Now, one additional thing is that for the hadrons, it can also deposit some fraction of their energy in the ECal, which actually complicates the identification of both electron and photons in the ECal. So what additional information that you can use to single out the electron, photons, and the hadrons is that first thing is that for electron and photon, the electron will leave track in the tracker, and whereas the photon will not. So you can use this idea to find out whether for a cluster, means when the this electron or photon deposits energy in the ECal, it forms a cluster. So you can, for electron photon discrimination, you can actually use the information whether a photon, whether a cluster has a track, it can be related to a track, whether if a if a if a track is extrapolated, whether there is a nearby cluster, then you can then you can separate out that, well, this track, this cluster is because of the electron, whereas the one which doesn't have a track associated is photon, in a very loose sense. Then again, for the for hadrons also, you have a neutral hadron and you have charge hadrons. The same principle applies to them as well. The neutral hadrons will leave no tracking, it will have no trace. You cannot trace it in the tracker, but and for the charge hadrons, you will definitely have a track in the tracker. So this using these informations, you can define some logic so that you can separate out this electron, photons, and the hadrons in the using the calorimetric information. Okay. So this was what I talked about in the last talk. So these are all like a qualitative picture. Now we have to move to a more quantitative way, so that which are actually applied when we do the experiments, when we actually do the analysis. We need some quantification, right? Because these are kind of qualitative and hand waving type of way of saying, well, I separate out this from this. So we need a more quantitative and definitive algorithms to separate out the one particle from another particle. So before I go there, I gave you one assignment to do. I don't know if anyone tried. So just let me pause for a moment to ask: did anyone have a look to it? If, whether you could do it or not. If not, I'm obviously going to discuss this because this is needed for the subsequent slides. So I just if 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 you haven't tried, that's fine also. Anyone who tried it? Okay, it seems no. Okay, so let me do it for you. Means so it was a easy one. Means since you have already the idea of relativistic kinematics, you can just do a little bit of algebra, jugglery with the algebra to find the solution of this. So what was the problem? The problem was that if you have pions and kaons, and if you have a TOF detector, which has an overall resolution of say 80 picoseconds, this is a kind of some just rough number, and whether you can separate them at the momentum equals to 1 GeV, and you can take a length, that is the from their point of production to where they are intercepted at the top, is equivalent to some equal to some Alice top radial position, which, if I remember correctly, is like 3 meters or something like that. Okay, can be something of that order. And then find out the limiting value of P beyond which you can no longer distinguish. Okay, so this was the formula. This was the basic formula that I already told you in the last talks. So if you have a pion and kaon, which which I note or which I write here as v1 and v2. So you can take either v1 as for the pion velocity or v2 as the kaon velocity or anything that you like, or vice. And then if you calculate the relative time taken to traverse a certain length, which is the length it takes from the point of production to the alley stop, then what is the time separation? What is the time gap that is needed? So that is related to the that you can mathematically formulate like this: L by C times 1 by beta 1 minus 1 by beta 2. So beta 1 and beta 2 are the velocity of pions and kaons, or pions or pions. That doesn't matter which one you want to take, you can take. Now you have to calculate if you take pions and kaons of momentum 1 GeV, whether your detector, which has a resolution of 80 picosecond, can separate it out or not. So from this relation and using the knowledge of your relativistic kinematics, actually, which I have spelled it out here. So you can take the pion mass as m1 and its velocity as beta 1. Sorry, I forgot uh, to convert it into mathematical notation. Sorry, and the energy E1 as m1 times gamma 1. Similarly, for kaon also you can write it like this. And then you this is the important part, that their momentum are same. So P equals to m1 beta 1 gamma 1 and m2 beta 2 gamma 2. And then you can replace, since you have seen that E1 equals to m1 gamma 1, so you can just replace m1 gamma 1 as E1 and m2 gamma 2 as E2. So you will get beta 2 times E2, and P equals to beta 1 times E1 equals to beta 2 times E2. So from that, you can actually convert beta 1 as P by E1 and beta 2 times P by E2. Now, when you replace or when you substitute these beta 1 and beta 2 in terms of P by E in the above equation, you actually get this equation, the equation in the last line. It is in terms of E, and then you can easily rearrange it, or you can expand it in terms of this equation, which you know very well. That is, it's the p square plus m
Hello,
square.
sir.
And yes, yes,
Hello.
yes.
Sir, why you are keeping this P same for both the particles?
Oh, so because you see, this is how we measure, right? We measure the response as a function of p. So you see these bands. So they, for a particular p, these particles are separated. So if you go, so suppose if you take pion at 1p and the kaon at another p, of course they will be separated, but you cannot have an apple to apple comparison. Because if you suppose you want to compare them, that in terms of in a way that that your length is fixed, the point from where it is produced to the point where it goes, that length is fixed. And then you want to have something which is related to their velocity. So if you change the momentum, then because from pion to kaon their masses are same, then their velocities are also changing. So if you change the momentum also, then all the three quantities are changing. So you keep one quantity fixed. Is that
Thank you,
clear?
sir.
So you keep
Yes.
one of the quantities fixed. So in that case is the momentum. So you keep the momentum fixed, because if everything changes, then it is difficult to represent them this in a compact mathematical form. Of course, you can do that, but it is not so easy to mathematically, or compact mathematical representation is, it's little bit difficult. So let's come back. So once you have this relation, then you can expand it in terms of this relativistic expansion of the energy, that is p square plus m square and the p square plus m2 square. And if you assume that the momentum of the particle is much larger than the mass of the particle, then you can have a more easier or a compact notation where you can you can directly relate the time difference to the masses of the particle. Okay, so with this assumption in hand, you can actually directly relate the difference in the time taken by two particles in terms of their masses. So one objective of taking a fixed momentum is that that you want to have uh, the relation in terms of the quantities which are very well defined. Okay, by that assumption, actually you land up in an equation where you definitely know this the quantities that the input quantities. Okay, so you know the L, you know the P because I have fixed the P, and now the masses are definitely we know from that the mass of pion and the mass of kaon. Now, if you substitute the values here, what you get is that the delta T that you measure is much as a very large quantity, maybe very unreasonable, but for the sake of explanation and the simplicity, so you get like a quantity which is much greater than is about 1000 picoseconds, and this is obviously much greater than the your detector resolution, which you have taken considered around 80 picoseconds. So if you want to quantify whether the time separation you get and your detected resolution, so if you consider the 80 picosecond as a sigma, then you get about more than 10 sigma separation between the time that the separation of pion and kaon. So this is a kind of quantity or quantitative way to say, well, if my detector resolution is this, and if the relative time difference taken for two species to arrive at the detectors is say this say if the relative if the time resolution is say x, and the relative time taken is say 10 times of the x, so you can say so the my two signals are separated by 10 sigma separation. So this is a kind of quantitative way to say to measure your quantitative way of manifesting your measurement. Okay, so is this clear to uh, some of you? Because this concept I will carry forward in the subsequent slides. So if something is not clear, please speak up.
Yes, sir, it is clear.
Okay, thank you. So please don't take the numbers very seriously. These are just for demonstration. Uh, okay. Now we move towards the actual quantification of the particle identification as we do it in the experiment. So what? So those who are already analyzing data, they must be quite familiar with this. So what is this? So first of all, when you get the data, you have a event, and then within the event you get some tracks. And then you analyze those tracks, and you analyze those tracks to extract the information about their kinematics and the also the information about the part PIDs. So how do you do that? How do you extract the information about the PID? So, since I have already introduced to you about the concept of nSigma, so it is like this. If you define something like this, so the here chi is a particular detector response, which can be your TPC-DEDX, it can be your time of flight beta, it can be your Cherenkov angle, it can be your transition radiation DEDX, anything. So this X is a kind of detector response of a particular species. So here I means you this I stands for a particular species. It can be pion, it can be kaon, it can be proton. Means those particles which gives a detectable signal in your detector. And then you take a difference, you actually calculate the difference between the signal or the response you measure in your detector and what is the expected response in that detector for that species. And this expected response is obtained from Monte Carlo, or also from previous experiments or the test beams that are done to in order to test the detector performance. So this is something that is that is not that in general, that may not be the part of the your analysis. That has been done by someone else, like from Monte Carlo, either from the Monte Carlo or from the test beam analysis, where they particularly measure this expected response. And then there is one more thing, that is the expected resolution. Because if you get a signal, that signal will always come with a resolution, because it is not like a delta function. Ought to be a in the simplest case, a Gaussian distribution. And so as in the case of previous the mathematical representation that I gave, that picosecond, the time resolution of your top was 80 picoseconds. So this can be a quantity something like that for a particular species, say for pi. And with this quantity, you can actually we can actually quantify, or you can actually calculate some quantities like nSigma TPC and nSigma TOF, which is defined as this. So DDX for a particular species, say pion, if you take it from here, this is what you measure in your experiment. This from the analysis, this is what you get. So you plug in here, and DDX expected, which somewhere in the database is available, and you plug in here, and the sigma DDX, which is also available, and you calculate the n sigma. Okay, so and also a thing you can do for the top, which has means the similar technique of doing this. And with these quantities, this n sigma TPC and n sigma TOF, you can actually separate out different species. And you
Yes.
separate out.
Excuse me,
Yes,
sir. So,
yes,
sir,
please.
I have a doubt. It is always the case that detector response will, X measured will be always greater than X expected.
No, actually, this is a mod.
Yeah,
It is
yeah.
a
There should be a mod. Yeah.
it is a mod.
Okay, okay, sir.
So so it means if you want to have obviously, thank you. So if you want to have a positive definite quantity, it should be a mod. So depending upon this n sigma, you can actually cut out a region which is of your interest. You think that, suppose if you give a n sigma of 2, you get this region in your of tracks, which are like, which you can call as a pion candidate. It is safer to call them pion candidate, which I will come later why I call them pion candidate. Because you are quite sure, yes, they are pions, but you cannot be 100% sure that they do not have the contribution from other species. So with a particular value of n sigma cut, say if you give n sigma TPC less than 3 or less than 2, similarly n sigma TOF less than 3 or less than 2, you can separate out your the particle species that you want to you intend to separate. Okay. Now the question is, what is the best choice of your n sigma value? How do you judge that? How do you decide that? What n sigma value should I use in order to separate out the particle species, different particle species that I want to separate? So for that, there is a quantity. I have shown this for TPC. Actually, this is say this can also be constructed for TOF. So this is called the separation power. Again, these are extracted, or these are calculated from Monte Carlo. So this separation power is the which actually quantifies at a given momentum range two particles, any two particles, what is the minimum sigma of deviation that you can achieve at a given particular momentum and for a given resolutions of those two particles. So this the left bottom plot is for TPC. TPC, I mean the DEDX, and the right one is for top. And you can see the separations from different particles are there, like electron to pion, K2 pi, and K2 proton. And similarly for the top also you see what are the separations you can achieve at a given momentum with the top detector. So with this information in hand, you can actually decide, if not very precisely, you can actually decide what is the cut value that you can give in order to separate out your species. So having said that, let's now move to another thing, is the combined PID. So far what I was talking about is doing the PID with one particular detector, but this may not be a very realistic case. Sometimes you need two detectors to have a more efficient or a more better way of achieving the separation. Now, how to do that? The most common way that those who are doing analysis, real analysis, they know that you use both the informations from TPC and TOF. Okay, so when you use both the informations from TPC and TOF, and you make a two-dimensional histogram, and I presume that by now all of you know what is two-dimensional histogram is. So here I have plotted in the x-axis is the nSigma TOF, and in the y-axis is nSigma TPC of different the tracks that I get. And you see a very nice thing. You see okay, so let me mention, these n sigmas are calculated relative to pion, so that's why pion is located at 0 0. Okay, so when I plot this n sigma TPC and n sigma TOF in this two-dimensional histogram, what you get, you see a region of three different region, at least you with the naked eye, you can separate three distinct region. The one which is quite far away is the proton. The one which is closer to pion is the kaon. So you see the three distinct regions you can actually identify from this plot, and this is a very good way to visually understand how your particle selection works. Now, based on this two-dimensional plot, if you want to actually do the selection, what you can do, you can just cut out, suppose if you want to, for the sake of easiness, if you want to cut out the proton, which is quite far from pion and kaon band, you can just cut a circle around this using this formula, right? This is the formula for for locus of a circle, right? R square equals to x square plus y square. So if you define something like that here, and if you cut out this region, you will get a more or less a sample of the candidate that you can call them proton. Similarly, if you have to be little careful for kaon and pion because they are merging. So if you also define something like that around this kaon or around this pion, you can also cut out your, or you can also separate your pions and kaons. Similar, and then I have showed it. So just I go back to here. So you can see this is on a particular PT range. Okay, so it is like 1.5 to 1.75, this PT range. And now when I go to a relatively higher PT, you see the change in the characteristic change that you see in your response. You see the proton bands were quite far away. And when you have increased your momentum or PT, which is like 2.5 to 3, the the those the distinctness of those different regions starts to disappear. Get it starts to fall on each other. It starts to collapse, and this you can also understand from the individual detector response, that is DDX versus PER of beta. So this combined PID approach can actually give you a more handle to do the PID selection than the individual ones. Because first of all, it is rather easy to visually to, to visually understand how well my species are separated, and obviously then you can have your mathematical formulation to cut out the different particles. Is that okay, or am I going too fast?
Yes, sir.
Okay. Now move to one thing, that is the statistical PID. So one thing I forgot to mention is that the thing that I was telling until now was for track by track PID. Means if you want to identify each track and assign them certain PID. So all these methods are for the track by track PID, which you need for some analysis. Like when you suppose if you want to calculate V2 or RE, essentially V2 or something like that, where you require exact identification of a track. There you actually use this kind of methods. Now there is one more method of doing this, is the statistical PID. So now if you see that your detector response, the separation starts to vanish as you go towards the higher momentum. Like you can see from this plot, when your momentum range or the PT range, when I say momentum, it means PT. So the momentum range, when you have a lower momentum selection, your particles are very well separated. And once you increase the momentum range, the separation starts to vanish. So it becomes increasingly difficult to define such formula that define some radii where which you can actually draw or cut out around the center to separate out your particle species. You will start having contaminations. Your pions, your protons maybe mistakenly identified as kaon. Your kaons may be mistakenly identified as pions. Your pions can be mistakenly identified as kaons. So this thing starts happening. So it gets really complicated and difficult to do a track by track particle identifications once you start going towards higher momentum or higher values of PT. So in that case, what is done is the statistical PID. But the statistical PID requires some a priori knowledge. You cannot just do the statistical PID immediately from the data. So what you do, you just project any of your detector response, say DEDX. So you can see these projections of DEDX, and then you use your a priori knowledge. If this is my DADX, if I have a Monte Carlo sample where which also reproduce the similar DDX, what are the centroids, or what are the centers of pion, what are the centers of kaon, and what is the mean position of pion, what is the mean position of kaon, and what is the mean position of proton. That knowledge you have to hire from your Monte Carlo information. From that you have to use that knowledge, and you can do some kind of Gaussian fittings of that curve. It is kind of three simultaneous Gaussian fittings constraining the mean and the sigma from the a priori knowledge. You can extract actually the yield. Means under this peak, this is a peak, quite a broad, the black curve, which I am trying to show by arrow. This black curve is the region that has everything. Your pions, kaons, and protons, everything are there. Now, you use the information based on the Monte Carlo information. If there is a pion, what would be this mean position, and what could be its sigma? So you try to constrain your Gaussian, individual Gaussian fittings with that information and try to do a best fit. And once you have done the best fit, then from this individual fitting components, you can actually extract the what is the, if you have a total integral, what fraction of the total of that integral is from pion, what fraction is from kaon, and what fraction is from proton. But be very cautious, because this require a very precise or a very accurate a priori knowledge. If your the knowledge that you hire from your Monte Carlo informations, or that if that is not properly tuned, you are certainly going to land up in to a wrong results kind of thing. So this kind of statistical PID is generally done at the higher momentum range, where the separation is not sufficient to do track by track PID at the track by track level. And also this for the physics application, this is applicable to the inclusive measurement, okay, where you just want to know the yield of a particular particle. So having said that, now I move to one of the important part, which all of you know and all of you use, is the efficiency and contamination. So what is this efficiency and contamination? So for efficiency means very means primary or elementary definition means, if you throw say 100 particles, to in a detector, how many of them you get back after passing through the detector. So if you get back kind of 90 particles after passing through the detector, then the detector is 90% efficient. This is kind of a very simple and trivial definition of efficiency. Now for PID, it is a bit complicated, because along with efficiency, there is also another factor that is called the contamination. So you see, this is a very common way of representing the PID efficiency. You have a three-dimensional matrix, and the diagonal components are the efficiencies of the particle. That is, you see efficiency of pi means efficiencies of the diagonals are the pi, kk, and pp, and the off diagonals are what we call is a misidentification fraction. So suppose I take efficiency of pi k. So this one, suppose. So this is something like that. What fraction of kaon may be misidentified as pi? Because you do some kind of you set up some kind of algorithm to do the particle identification, and those are not 100% foolproof. So obviously some of the kaons which are actually kaons will be identified as pi. Similarly, this is something like that. This efficiency k pi means what fraction of pions will be identified as, will be misidentified as kaon. So this diagonal elements stands for the thing that I just defined, and the sorry, of diagonal elements, and the diagonal elements corresponds to the efficiencies of those particles. So these are defined something like this. So if you have a number of particular particle, and if you identify those a as a, so suppose you throw 100 pions, and how many of the pions you identify. So this is the number. So this is the efficiency, and uh, these things are somehow calculated from calculated from the Monte Carlo information. Again, okay, is that clear?
Yes, sir.
Okay, so okay, so next I move to the contamination. Now this is a bit tricky. Why contamination is bit tricky is because since you use the Monte Carlo information, if your Monte Carlo is not properly tuned to the data, your contamination may not be correct, because this Monte Carlo you have seen the contamination as I have defined. It is the this off diagonal times the multiplied by the uh, true yield of a particular particle and divided by the all the particles that you have in the denominator. So this true is the absolute yield of the particle. So, since you use Monte Carlos to determine this contamination, if these yields are different from the yield that you have in the data, then what you will get is the wrong values of contamination. So when you are actually calculating the contamination, those who work in alleys or stuff, they may know the Monte Carlo responses are tuned to data. What do you mean by tuned to data? That basically by tuning, this tuning means that the detector response, what you have like ddx or tau beta, all these detector responses are adjusted in a way so that they are very close to the detector response in the data. Because all you do is that you have a event generator, and then you pass it through GR4 model of your experiment, and then you get this detector response. So you have to tune the detector response in such a way that the final signal or the simulated signal that you get are very close to data. And also, one thing is that the absolute yield, the true yields of your Monte Carlo are also scaled or adjusted in a way so that they are also very close to data. So in this way, actually, you can avoid going into getting wrong contamination numbers. So this is the way actually it is done when you estimate the contamination for suppose if you have measured pions using some algorithm, and then you can there is obviously chances that that pion will have contributions from kaons, and also as if you measure kaons, that will also have chances for that it is contaminated by contributions from pions. So having if you want to estimate what is the level of contaminations, this is the way you do. Okay. So these are some just generic definition of this. I have not given any plot for this because the the plots are depends on the and are very analysis specific. So this is the general formalism. So those who do analysis, just one thing for them, that when you actually calculate the contamination, you have to be very careful, because it very much depends on your Monte Carlo tuning. If you are using Monte Carlo to do to estimate your contamination, whereas the misidentification fractions are independent of the absolute yield. So what is generally suggested is that you calculate the misidentification fraction, then you go to an independent measurement where you know the particle yield. Suppose someone is doing a correlation measurement, and they are doing correlation with identified particle, and if you want to measure the contamination, then you calculate the misidentification fraction first, then you go to the people who are doing spectra, and you take the yields from the spectra, and then you plug in this formula, and you calculate the your contamination level. So this is the general prescribed way. Could be some other ways also, but so the thing that I want to emphasize here: be careful when you calculate the contaminations, because the very definition of contamination has the yields that are very much dependent on the choice that you make. With this, I think I am done. So this is the last slide. So thank you for giving, first of all, thank you the organizers for giving the opportunity, and thank all of you who logged in and stay tuned to my talk. So thank you.
Hello, sir.
Yes,
Sir, I have few questions.
yes, please go ahead.
Uh, Sir, can you please go to the slide 28?
Yeah.
28. It's actually, uh,
This is 28.
okay, sir. Yes. So, sir, actually, my question is not from the slide.
Mhm.
It is a general question, sir. For 10, we do in start, that is, for top PID, we put some mass square cuts.
Yes, yes, yes.
But you have not discussed about that. I had actually some doubts regarding that.
Okay,
So, sir,
first tell me what are your doubts? Means mass square cut
so,
is
sir,
something. So if you can be a little specific, why you use the mass square cut? Means is for the star top measurement is the general scheme of doing the particle identification is this or this is different?
no, sir. Sir, actually, first, my question is why we do mass square cut,
Mhm.
and then my question is, sir, for pion case, I have seen that we sometimes we take that mass square is negative. That is,
Mhm.
why that negative mass square mean?
Okay,
My main question was
so
that, sir, actually.
okay, okay. So you see, this term, this because see, first of all, the top measures the time, right? The separation in time, and this is somehow related to the differences in the mass. Okay, so if and so obviously your measurements will have error, your detectors are not perfect, so you can obviously land up with the situation where you get the response or the signal in such a way that when you determine the mass square, so first of all you determine mass square, you did not determine mass, so you do not land up with the problem of imaginary numbers or so. That is why you take mass square. So your detector responses should be
Hello, sir, you are
maybe
not
such.
audible.
Oh, I'm not audible now. Hello. Hello.
Yeah, you're audible, sir.
Okay, so should I go ahead? I don't know who asked the question.
Sorry, sir, I missed your voice somehow. I'm Ashwini from Aiser Barampur.
Yeah, yeah. So first thing is that you are defining the quantity as mass square. It is not mass. Okay, so the when you are determining something from your detector responses, and the detector responses are not perfect or not ideal, so there are chances that you will have the mass square terms. It is negative, and it both because it will have a distribution. It's a Gaussian distribution about say suppose you if you are measuring the mass square of muons or electrons, then you will have some distributions of this mass square which will be both left and the right of the mean mass of the muon. So there are chances that you get this mass square as negative because your detector response is such that when you do the calculation, you land up in a situation that gives you a negative mass square or negative parameter of the quantity that you want to calculate. And secondly, I think because I have not used this mass square ever, but from some knowledges from somewhere, this mass square cut is given to remove some kind of background. Means if you have some idea about say your track is going to say pion or something like that, then you can formulate some mass square versus momentum quantity, and you can give a cut if the mass squares versus momentum starts to diverge far from your expected pion mass. So this way you can reduce your background.
Okay, sir. Sir,
Does that
so
answer you?
your point is that actually, sir, I see the formula for mass square, which is about p square whole into 1 over beta square minus 1. So when we are
Mhm.
calculating that beta, we may have some uncertainties in
Yes.
t and l. So which may lead
Yes,
to
yes,
this conflict. So
yes,
that is the point.
yeah.
So, sir, it is just a general question that
Mm.
if the mass square becomes negative, we may go to the conclusion that B is greater than C.
No,
So,
that you can't, right?
Yes, sir. That is the thing.
That is
That
unphysical, right? That is
yes, sir.
that you in measurement you have to means you can measure anything, but then you have to apply your knowledge and the physics that whether that is physical or unphysical.
So, sir, that was my doubt. Ki, if we are putting mass square is negative, so if we go to the formula, if
Mhm,
our mass square is negative, then we have 1 over beta square minus 1. 1 over beta square is less than 1.
mhm.
So 1 must be less than beta square. So we
So
may
your
have
beta square is greater something means
greater
your
than
velocity is become something which is greater than speed of light.
greater than c.
So
So, sir,
yeah.
if it appears, I got your point that the negative thing coming due to the that uncertainty in delta t and delta l.
Mhm,
That
mhm,
I got your point. But, sir, if we are seeing that we are getting an unphysical result, so
mhm.
how we suggest that is, this measurement is not done today, na? But people are using this mass square code since beginning.
Yes,
So
yes.
how people approve this that we could take mass square from
No,
negative
no.
0.2
So
or
first of all, tell me, when you get the mass square negative, do you accept that track in your in the subsequent steps of your analysis?
yes, sir. For like for our analysis, we take our pion track. For pion track, we
Mm-hmm.
take mass square in between negative 0.2 to 0.15.
Mm-hmm.
So that case, it came to my mind that how we are taking this minus value as our
Okay.
third.
See, I cannot give you a very pinpointed answer, but maybe
Yes.
from some estimates they have the knowledge that even that is negative, but it corresponds to pi. Means the pion mass square because of your experimental uncertainties it can be negative, but that is not very unphysical. Maybe from some independent source they have somehow obtained or calculated this way that if you just throw pions and you calculate mass square, then also there are chances that your mass square will be between this can have some negative values. So maybe from that knowledge they have incorporated this range. But yes, you are correct. If you are if someone is doing this for the first time, he or she should actually cut out the negative part of the mass square.
Mm, and okay, sir. Thank you, sir, very much for this. Sir, another from slide 32.
Okay. Mhm.
Sir, I'm still seeing you.
Oh, you will take it will take some time. There is a latency.
Okay, sir. Sir, now I got this. So,
Mhm,
sir, a similar thing I have also done that is for top efficiency case. When we are
mhm,
measuring our top efficiency, so
mhm,
what we do that we project the mass square.
mhm,
We have 2D histogram that is mass square and PT. So we
mhm.
project our mass square in different PT bins.
Yes, yes,
So,
yes.
so, sir, even I can see that from your top panels, first and two
Mhm.
panel, the Gaussian fit is not. I don't think it is good, sir, because you can see the tip point is not matching in the
Yeah,
first
of
case.
course,
Yes, sir.
of
So
course,
that case
of
also,
course.
sir,
There are fitting
happens with me.
uncertain. There are fitting uncertainties. That's why this is what I said. This is a kind of a way which you use when you are limited in the track by track PID. This has a lot of uncertainty. That's why I use the term. You have to kind of do a best fitting. So you
So,
have
sir,
you have to
during
fit
fitting, what I do that I know the what is the mass of ion and kaon, proton,
yes,
whatever.
yes. You
So
use your a priori knowledge.
so, sir, what I do that I said that I initiate my variables that when I'm fitting the Gaussian,
Mhm,
I start with the mean from the mass square of pan. That is what I know. That is square of
mhm,
0.1414.
mhm, mhm,
Um,
mhm.
so, sir, even after doing that, the tip usually don't match in some PT beams. Even
Yes,
also the sigmas, my fit goes in one way, and I'm getting my data points in some another way. So
yes.
in that case, should I take that mean or sigma or not? Because my root says that this fit converges and everything is all right. but
Yes.
I could not satisfy myself that if I'm doing right thing or wrong, should I accept this or not? Not.
Yeah, yes, yes. This is obviously a problem. Means if you are doing it just based on data, you have no guidance, right, to
Yes.
understand whether it is going right or wrong. So one thing I can suggest is that if you have if you have a Monte Carlo data where for which this in a top PID or the top beta is mass square cut is available. So in the Monte Carlo, you definitely know exactly where what is what. From there, you can first test your fit at the Monte Carlo level. So you can design a template first, and then you use that template in the data. So this could be one way of getting some kind of confidence that whether your fitting is good or whether you are going in the right direction or not. Otherwise, you are correct. This type of measurement has a lot of uncertainty. So generally, it is prone to uncertainty.
So, sir, during measuring the top efficiency, what I am doing that I fit this with multi-Gaussian as we have three
Mhm.
particles.
Yes,
I
yes,
fit it with
yes. Also, you
multi-Gaussian.
see this one is also multi-Gaussian, three
Yes, sir.
Gaussians.
Yes, sir. Yes, sir. So, sir, for example, I am measuring for pion. So,
Mm-hmm.
what I do that I from the Gaussian fit for pion, I got my main and sigma, and
Mm-hmm.
uh, I took the ratio of what area comes what the Gaussian area comes under my curve divided by what the area comes in 5 sigma, because I assume that in between 5 sigma I got complete 100% Gaussian
Yes,
area.
yes, yes.
So sir, sir, I'm doing this kind of thing.
Mm-hmm.
So sir, what
Mm-hmm.
happens when I'm doing for pion, I get it's approximately above 99%, which we should expect that our type of is 99% efficient. But sir,
Mm-hmm.
when I'm doing this for the same thing for Kaon,
Mm-hmm.
after 1 GB,
Mm-hmm.
the efficiency decreases drastically. Like up to 1 GB PT, I'm
Mm-hmm.
getting approximate 99 or 98%. But
Mm-hmm.
after 1 GB, it is decreases to 70%, 60%, which should not happen. It is obvious. We should not expect that our top is this much inefficient.
Mm-hmm.
So in that case, I could not satisfy myself that where the fault is. Is the fault from I'm doing from the multi quotient fits where I'm extracting my mean or sigma, or something else I am doing. So
Yeah.
sir,
So so
that is one
uh, so
problem.
uh, so so what one thing that I can suggest is that right now is that if you have some MC responses where you know exactly means first thing how you tested your fit means there should be some way because since this is a kind of complicated fit you have three Gaussians and then you do a multi Gaussian fit. Have you tested in with some benchmark?
No, sir, I have not.
So at least one thing. I think
So by
maybe in the
benchmark,
peripheral collisions, where means see even you take the multi Gaussian if your distribution doesn't have a kind of peak structure, this Gaussian peaks, it is very hard to converge. That I that
yes, sir, yes, sir. So for
like
low PTs,
like a.
we have distinct peaks. That is in that case no problem. But after
Mhm,
1 GB, where
mhm,
they kind of like these figures where they
mhm.
merge together. In that case,
Yes,
the
yes,
fitting I'm facing very much difficulties during fitting.
yes. So
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 and the
yes.
discrepancy comes after that PT range. So
Mhm.
that is one of my problem which I'm facing currently.
Okay, so I means obviously I cannot give you a solution offhand,
Yes,
but what I can suggest you is that try to have some benchmark means because when the peak starts to collab or merge, it is really difficult to do a good fitting. So in case if you have some benchmark where exactly you know, there you can first test your fit and then you can apply that to your data. I think that way you will first of all get the confidence that okay my fittings are working well,
yes, sir.
otherwise there are too many free parameters.
Yes. So, sir,
Just I'm interrupting you. And also the sigmas. So how do you constrain the sigmas?
yes, sir. So no, I am not putting any constants on sigma.
Okay.
So it just adjusts from the data
So
point.
your sigma is free, means is a free parameter, right?
It's a free parameter, yes, sir.
And
So
do you fit at one stage or you do multiple times? Means suppose you do fit once, then you extract the parameters and you use these parameters as an initiator for the next step, and
no, no,
then
no,
again
sir,
you
no,
fit.
sir. In every loop, I am doing it again and again. Like our sigma is not the same for everyone. Na? Like for low PT, we get sharp peaks,
No, no,
but
no, no, no.
when
I'm
we
not
go
talking
to
about low PT or high
yes, sir.
PT. I'm talking
Yes,
about
sir.
suppose in a PT range, suppose take a high PT range where your fitting is not good. So you fit the graph once, or you fit the graph say two or three times.
No, no, sir.
Means
I'm fitting it once.
so one thing you can also try, means I don't know whether it will work
Yes,
out or not. So you
yes,
fit
sir.
at the first stage, you get the parameters of
Yes,
from the feed. Then you use those parameters as the initiator at the second stage,
okay,
again you fit it. So maybe
okay,
that way it will help to improve one way, and another way could be if you somehow know the expected sigmas of pion or kaons or protons in that momentum range. I think that way also it will help to means constrain your sigma, because
yes,
when the peak starts to merge, your sigmas will fly off just because your sigma
yes,
is unconstrained. It doesn't know where to stop.
yes, yes, sir. I got. So, sir, can you please help me from where I can get this informations like for kaons or pions in
Oh,
this
but
PT
it's experiment specific. You are in star, right?
is like what you do for Alice that can do
Oh,
for
Alice has this information. They have this Monte Carlo informations. They are tuned to data. All these informations. It's unlike Star. They do the Monte Carlo production of means Star does the embedding, right, and Alice
okay,
does the entire Monte Carlo production with all kind of detector response convoluted and all those things. So this is from Alice. So I don't think that will be available to
yes,
you
yes.
from Star. But because I have not done PID analysis in Star. So maybe you can check with the experts from the Star.
Okay,
That way you can get a more pinpointed answer.
okay, sir. Thank you very much, sir, for your help.
Yeah.
It helped
Thank
me
you.
a lot. Thank you very much, sir.
Anyone? Anything else? Okay, Siddhartha. I think I am done. If there are no more questions, Siddhartha.
Hello, Subikash da.
Ah.
Siddharth sir actually just went to registered office for some important meetings. So
Oh,
he
okay.
requested you to conclude the.
Uh, he requested me. I forgot actually. Sorry.
Oh, acha, acha. Okay,
Oh,
sir, you
okay,
can.
okay.
Okay.
There is the organizers. So I need
Ah,
not to.
okay. Sorry.